Lab 1, Newton's second law. The purpose of this lab is to observe the motion of some object that is moving at the same speed without changing direction. In this case, a Crayola marker with a mass of about 15 grams or 0.015 kilograms was chosen as the observed object. The program tracker allowed for experimental data of the position versus time to be observed. In order to do this, the first and last frames of this original video were not used, as it was decelerating, which will be explained later. The objective of this lab was to understand Newton's second law, which is change in velocity in meters per second is equivalent to the net force in newtons divided by mass in kilograms multiplied by change in time in seconds. Here we were solving for the final velocity, given the rest of the information. Later you will see that the results proved to be linear by the computational model, yet the observed data was almost linear and differed from the computational model, which will also be discussed later. According to Newton, an object will only accelerate if there is a net force, or in other words, if there is an unbalanced force acting upon it. When the net force is equal to 0, the mass is not significant according to Newton's second law, nor is the change in time, since it is being multiplied by the net force divided by the mass. The only thing that remains in this equation is final velocity is equal to the initial velocity, meaning that, theoretically, if no net forces are acting upon an object, the velocity will remain constant for any amount of time into the future. This law can be shown by the computational model created using VPython. The code required certain parameters to be specified in order to use Newton's second law to compute the predicted final velocity. The length of time for the desired prediction, 1.166 seconds, was initialized as well as the mass and its initial positions. The vector for net forces was set to 0, and using these variables, the code included Newton's second law. Since the tracked object rolled from left to right, as you saw earlier in the video, the resulting graph was a line increasing in both positive axes. If the axes were switched, and the marker was going from right to left, then the graph would have been reflected over the x-axis, meaning that the position data would be negative. Since the computational model is a prediction of the future based on Newton's second law, and the net force vector is equal to 0, it resulted with a graph of perfectly straight line showing the theoretical relationship of position versus time with constant velocity. This linear relationship, however, was not the case for the observed model. As you can see here, the observed model is almost linear, yet it shows that the computational model overestimates the data more and more as it approaches the end of the specified time interval. The reason for this difference is because the net forces in this lab were not equal to 0. Watch the video of the marker rolling once again. Friction played a role in this motion, which the computational model did not account for, which caused the graph to curve slightly downward as it was decelerating. Also, the position of the marker slightly shifted up towards the end, which would also explain a difference between the two models. The net force being equal to 0 does not mean that no forces are acting upon the object. Gravity is acting upon it. But what counterbalances the gravitational force is the force that the table is exerting on the object. These two forces acting upon the Crayola marker cancel each other out, causing the net force to be equal to 0, and therefore cannot be seen. This concludes Lab 1.